Okay, time to get started. So, picking up where we left off last time, so we were talking about surface integrals, and just remember surface integrals are actually a lot like line integrals. I mean, they're obviously different, right? I mean, one's about stuff that accumulates over a surface. The other is about stuff that accumulates over a curve. Geometrically very different, right? But it does still have the same sort of underlying idea of the whole is the sum of the parts. So these constructions apply to only quantities that have that feature of being accumulating quantities. Cannot emphasize that enough. Anyway, we wrote down definition. We did some examples. We talked about how to compute it by pulling back through a parameterization, just like with line integrals. Let's see here. We applied it to a quantity with an orientation, namely flux, kind of like we did with line integrals, to work. Again, two scalar quantities, but they depend on orientation, and thus created two new kinds of integrals, right? So with line integrals, we had inadvertently created vector line integrals. Turn out to be pretty natural in a lot of ways. And now, not long ago, we recently created vector surface integrals. Again, useful in, we haven't seen a lot of the uses yet, but certainly that's how we compute flux through a surface. That's how we measure how much fluid is flowing through a surface, etc. Okay. All right, so hopefully no surprise, we have symmetry that we can take advantage of. So in particular, here's another odd symmetry theorem, this one for scalar surface integrals, and if your integrand is odd, and if your domain is symmetric, and I emphasize both of these conditions have to apply, and it's got to be the same plane for each. And I'm going quickly through this because you've heard this little speech several times. I've lost count at this point, 5 or 6 times, right? It's the same ideas, just now applied to scalar surface integrals. If these conditions are met, then the integral is equal to 0. And again, very familiar idea, just like we've seen before. Tempting to say yawn, but again, there is a landmine that y'all have to watch out for. So please do be careful about this. This is only for scalar surface integrals. There is no odd symmetry theorem for vector surface integrals. There is no odd symmetry theorem for vector surface integrals. Saying it twice because it's important. I've seen students who are, rightly enthusiastic about the idea of odd symmetry theorems. Wonderful. I encourage that. I think that's important. And then try to apply it to something where it doesn't make any sense. And it's a tragedy to see because the calculation just there's nothing about the calculation that's actually valid mathematical reasoning. So please do be careful about that. Now, why doesn't it work? Well, if you have a vector surface integral like so, keep in mind you can rewrite that ds vector like so. And now let's think about this unit normal that's kind of wrapped up inside of the ds vector, hidden inside of the ds vector. And look how it behaves in an example like this. And in kind of the same way that unit tangent vectors don't behave nicely on symmetric curves, likewise unit normal vectors, they just don't behave particularly nicely in terms of oddness on symmetric surfaces. And again, you look at these two vectors right here. These two vectors, are they the same? No. Are they negatives of each other? No. They're neither. And so if you're just keeping track of minus signs and cancellations, we're kind of out of luck on this. Okay. All right, now quick side note, there is a different kind of a symmetry theorem for vector surface integrals. It's more trouble than it's worth. By the way, there are various different symmetry theorems that can be stated, perfectly valid theorems, that I'm not showing you because they're more trouble than they're worth. Again, tough choices, you got to make decisions on what to spend time on. And some of those other theorems, I like to view it as you can get yourself into more trouble with them than you can get yourself out of. So anyway, that's a little side note for your consideration. Okay, pause. Questions. Anybody have a question about any of this symmetry stuff? Totally works as expected for scalar surface integrals. Doesn't work at all for vector surface integrals. Everybody buy it? Okay. Moving along. Okay, so I think this is a really cool little page here in the notes. This is not in the book. I really think it should be. There are some remarkably eyebrow-raising, unexpected analogies between vector line integrals and vector surface integrals. They're shockingly similar in a lot of ways. Now, ultimately, why is that? Well, because it turns out that both of them are just integrals of differential forms. They're just different kinds of differential forms. And so, if you understand differential forms, then you would look at this statement and say, well, yeah, I mean, of course, no surprise that they're so analogous because they are ultimately just two different examples of the same thing. But we're not going to talk about differential forms, integrals of differential forms. It's not what this class is about. It's a little bit too sophisticated, a little bit too high level, I think, for Math219. So we're left a little surprised that there are such strong analogies. And so, again, I think this is of good cultural interest, if nothing else, a little math culture. But that's not the only reason I'm showing you. I want to emphasize I'm showing you the following because these are a great learning tool as well. Okay, seeing that there are patterns and analogies will help you organize ideas in your mind. It'll help you use what you understand about line integrals to help you make sense out of surface integrals. And so, again, just, sort of from a learning point of view, from a keeping it straight point of view, I think this is really nice. And so I hope you'll benefit from this. So anyway, here we go. In both cases, we parameterize to compute. All right. In both cases, we talk about the derivative. When you're looking at a parameterized curve, the derivative is velocity. When you're talking about a parameterized surface, I'm going to kind of abuse the term here a little bit and call capital N a derivative. Well, it's computed as a cross product of two partial derivatives. It's not that far off from being a derivative, and depending on how flexible you're willing to be with language, maybe it's a kind of a derivative in a way. And let's look and see how those show up in the equations here. And now, by the way, the equations I have on the screen, nothing new. Those are all old equations that we've written down previously, that we've developed independently, separately. But you see the derivatives of the parameterization, they show up in kind of the same places. Okay. In both cases, you can talk about pullbacks. Right? There's a pullback size dt there. There's a pullback size ds dt there. And in fact, I'll leave those circled. Why not? We can see where those show up in the calculations. Again, of course, they're different. One's one-dimensional, one's two-dimensional, but they play analogous roles in the equations. Okay, whatever. Let's see here. We can talk about, let's see here, color choices. I'll use orange. We can talk about the unit vector, pointing in the direction of our derivative vector. So capital T, unit direction vector for parametrized curves. Little n, the parametrized unit normal for a parametrized surface. And let's look and see where those show up in the algebra. Again, totally analogous. What are the odds? OMG, right? It's kind of surprising, I think, that that everything kind of lays out on the page in exactly the same way. And you can just keep on going here. Let's see, we can talk about, I'll use blue, I guess, the size of the little piece of curve. You can talk about the size, little piece of surface. And those show up in analogous places. You can talk about the curiously convenient little vector here, dr. The curiously convenient little vector here, ds. And those play analogous roles in the equations, and again, you can just see where they sit in the equations. And remember, they also play similar roles geometrically. The dr vector points in the direction of the orientation, and its magnitude represents the size of the piece of curve you're talking about. The ds vector, exactly the same thing. It points in the direction of the orientation from your parameterization. And its magnitude represents the size, in this case area, right? But the size of the little piece of surface this time that you're looking at. So, wow, right? That's a lot of analogies. It's not a coincidence, right? So what you're seeing here is a consequence of some really deep water that we're currently sailing over. Right? Very sophisticated reasons underneath all this as to why all these analogies are there. Again, I do not expect you to understand why they're there, but I do hope that you will notice that these analogies are here, and I hope you will benefit from, again, keep helping you to keep ideas organized in your mind. As you're trying to make sense out of surface integrals, for example, notice anytime you see capital N, just think, okay, that's playing a role kind of analogous to velocity, in a way. It's the thing whose magnitude is the stretching factor, for example. Right? It appears in the equations in analogous positions. I think that's very useful for mental organization. And by the way, it keeps on going. If I can get my screen to cooperate, here you go. If you take this little color scheme I've created and just extend down to all of these equations that we've got representing, on the one hand, vector line integrals on the left, vector surface integrals on the right, and just, again, just keep going with the filling in the colors per the color precedent. Again, everything fits. The pattern is basically perfect. So, really cool little reality. Okay, let's see here. I'm pausing again. Questions? Anybody? Squeeze this back up to, here we go. Okay, moving along. Okay, that does it for 7.2. Off into 7.3. By the way, 7.3 is another huge section. It's another one that's going to take us several class meetings. There's just so much to do. Oh my gosh. Another one of these sections where I feel like it really could have been at least 2 sections, right? This is the Alaska of sections in this book. By the way, so I'm originally from Texas, and people from Alaska like to make fun of Texas in the following way. They like to point out that Texas is actually the second largest, not the largest state. Right? And so a lot of people from Alaska like to point out, we could split Alaska in half, and that would make Texas the 3rd largest state. Right? Because Alaska is just enormous. Anyway, so it's kind of the same for this section here. If you were to take section 7.3 and cut it in half, it would still be, each of them would be one of the biggest sections in the book in terms of content included. And how much stuff there is that needs to be talked about, and how important it is to the material. So why are you here? And let me go ahead and throw in, while we're on that topic, I've had conversations with engineering professors on a handful of occasions, talking about, what's important to engineering professors for engineering students to know about multivariable calculus. And the short version is that this stuff right here, section 7.3, this is what they need you to understand. This is the most important. Now, of course, you can't understand 7.3 if you don't understand chapter 2 and chapter 1 and chapter, let me keep going. I mean, a sizable fraction of the course is prerequisite to this one section. And we've been building up to it. But a great amount of why do you need to know the earlier stuff is because it's necessary to understand Stokes' theorem and Gauss's theorem. All right, moving along. We're going to follow the same pattern we have for a lot of stuff. We're going to talk about boundaries. Wrong mode. We're going to talk about boundaries, and in particular, boundaries. Remember, we talked about this before. The word boundary now means an oriented thing. The word boundary includes a specific standard, arbitrary to be fair, but standard convention on what that orientation should be. And you remember we did this when we were talking about Green's theorem, and we did it again when we were talking about various other theorems. And so yet another example, we've got to establish what the standard convention is, what we're going to use. And again, it's a little arbitrary, but it is very standard, and so we're stuck with it. So here's the rule. The rule is whatever point you're at on the boundary, and keep in mind the boundary is kind of the dividing surface between where the solid is and where the solid isn't. The rule is that the orientation is always away from the solid, away from the side of the boundary where the solid is, and into the side of the boundary where the solid isn't. Right? So like so. Now it's tempting to call this outward. A lot of people will say outward. It's not really quite true. Here's another example. You look at this point, and that's part of the boundary because it's part of the dividing surface between where the surface is and where the surface isn't. So that's part of the boundary too. And at that point, away from where the solid is and into where the solid isn't, it's not outward. Right? That's, I think you'd have to call that inward if you were going to describe that vector with one of those two words. So don't make the mistake of falling for the oversimplified answer. It's not always outward. Just like when we were doing Green's theorem, it's not always counterclockwise. Right? It's usually, certainly when you're going around the outside. But it's not always. So you got to be careful about, again, that oversimplification. Okay. Everybody okay with this? All right. Alrighty. Again, we're going to be looking at an accumulating quantity. By the way, again, you'll notice we talked about boundary orientations first, and now we're going to talk about accumulating quantities. You could probably guess what's going to come after we talk about accumulation. Just look back when we were doing Green's theorem and see what the next topic was there. We're going to be following the pattern very deliberately. My little way of emphasizing, underscoring how much these theorems are analogous to each other. So here's the idea. First detail I have to throw out. We're not talking about accumulation over areas. Now we're going to talk about accumulation over volumes. We are in 3 dimensions after all now. And volumes are the kind of regions that we're interested in 3 dimensions. So when I say accumulates over volumes, what I mean is if you take a whole volume, define your quantity on the whole, if you look at just one side, one piece of it, define your quantity on that piece. If you look at the other remainder, define your quantity on that piece. We need the whole to be the sum of the parts. Right? So notice specifically it is the volume that we're splitting up. And boundary flux has this feature. It's a little surprising, But sure enough, and the reason is that if I look at the left piece of volume, now keep in mind I have this whole lump. This is a solid three-dimensional lump. I'm cutting it in half. It doesn't have to be in half. I'm cutting it into two pieces. If you look at that left piece of volume, very importantly, volume. If I talk about the boundary flux for that volume, now what that means is I'm going to take that volume, I'm going to look at its boundary, which is a surface, and then I'm going to look at flux through that boundary. Right? Boundary flux is going to be, well, there's going to be a sort of a chunk of boundary flux on the sort of the left side of the eggshell, if you will. And then there's also going to be this, there's going to be this kind of, the cut face there, and there's a piece of surface there, and therefore flux to be discussed away from R1 through that piece of boundary surface also. So there's boundary flux on the left. Looking at that same on the right, if I look at this right volume, again emphasizing volume, and if I look at the boundary flux, so look at the boundary surface, talk about the flux through that boundary surface, well, there's sort of the right half of the eggshell, if you will, outward, loosely speaking. And then again, there is the cut face. Same cut face. But this time, away from the volume, away from R2, is going the other direction. And so, just like in the case of Green's theorem, just like in the case of the two-dimensional divergence theorem, right? What's in the middle appears twice, but with opposite orientations, and therefore those two surfaces, the integrals, the fluxes over those two surfaces are exact negatives of each other, so they cancel, right? And when you cancel those two faces, notice what you're left with is exactly the outward oriented boundary flux for the whole. So indeed, the whole is the sum of the parts. So this is an accumulating quantity. How are we doing? Everybody cool with this? Quick flashback. Let's see, let me clean up the mess. Quick flashback. Yeah, here we go. Oh, whoops, that wasn't in the right mode. Notice how similar that picture that we just talked about, how similar that is to this picture that we talked about back in chapter 6. Now on the left, what we were talking about back in chapter 6 was talking about outward oriented boundary flux on areas. Areas with boundary curves. Right here we're talking about volumes with boundary surfaces. So a little bit different, but notice how the diagrams, I mean, they look so similar. They're really, really similar pictures, right? And this idea of there being, there's a sort of a shared cut piece, and then the orientation's opposite on the two. I mean, it's really, really similar. Basically the same ideas. Okay. Alrighty. Okay, moving along. Let's see here. So we have an accumulating quantity. We long ago established cool stuff about accumulating quantities. I feel like I've said that enough times at this point, right? But any accumulating quantity, little details to be worried about, right? But as far as a really consistent strategy, I'll say, is that when you have any accumulating quantity, you can view it as being a kind of a stuff. You can talk about the associated density, and you can therefore write down an associated integral theorem. And again, same story. We have boundary flux is an accumulating quantity, so it behaves like a stuff. And okay, sure, look, we measured on the boundary, but again, I claim it happens in the interior. And again, old news, right? So we talked about this idea before, and it's a little bit weird to think about, but let's go back to this little discussion on the left that we had a while ago. about the fundamental theorem of calculus. Weird take on the fundamental theorem of calculus. But what this take on the fundamental theorem of calculus does for us is it completely demystifies this idea of, if you have an expression computed on the boundary, can it actually be happening in the interior? Well, of course it can. My gosh, change. You compute it, I suppose, f of b minus f of a by looking at the endpoints. Yeah, right, of course. But where does change actually happen? Well, you can see it right there in the graph. The change is clearly happening in the interior. Of course it is. The only reason it's not that obvious in the case of higher dimensional theorems, like what we're looking at here with outward-oriented boundary flux, is because it's dimensionally harder to draw pictures of. Right? But it's the same phenomenon happening there. Right? Certain quantities, accumulating quantities, even if they're computed on the boundary, they actually happen in the interior in some reasonable sense. Right? So when you're trying to digest, and again, I completely recognize that it's a big ask for me to suggest that you should think of outward-oriented boundary flux, flux that's computed on the boundary, you view it as happening on the boundary, for me to say, think of that as being stuff in the interior. I know that's a weird ask. Of course it is. Think about what we have on the left there. Think about what this same point of view on the fundamental theorem of calculus. Not such a big ask there, right? And there's something very analogous going on here. Okay. Alrighty. Moving along. So we got a stuff. When you have a stuff, you can talk about how, what's the density of that stuff. You can talk about stuff per unit volume. And here we go. If you look at a boundary flux, outward-oriented boundary flux, by the way, we very often will just call it flux in a context where, of course, we're talking about boundary flux. It's a lot of extra syllables to say boundary flux instead of just flux. So in this entire section, when we say the word flux, I probably mean boundary flux. Context will be your guide. Make sure to keep a lookout for that. Anyway, flux, something you can compute on a little piece of volume, divided by volume. By the way, I drew an area just because it's easier to draw, easier to visualize, but this is supposed to be representative of outward-oriented boundary flux through a boundary surface per unit volume inside of that surface. So this idea, flux per unit volume, is what we call flux density. Just like every other density we talked about, we have accumulating quantity. It's not mass, it's not population, it's not any of the other accumulating quantities we've seen before, but now a newly established boundary flux is an accumulating quantity. Accumulating quantity per unit size, in this case volume, that's a density. Okay, so very, very commonly used term, flux density. You're definitely going to hear that and see that. But side note, it goes by other names and notations. This is divergence. And long ago, we wrote down this formula for divergence. And I made this kind of apologetic assertion completely without evidence. I just claimed that, divergence represents, in some, per unit volume in some sense, to what extent is the fluid flowing sort of outward? And we can see that now. Right? We can totally see why that is. I mean, I didn't derive the algebra of this formula, but if you're willing to believe that divergence is flux density, then here's why it's outward flow. Because that's what flux is computing. Flux is computing the extent to which the fluid is flowing outward. right? The extent to which the fluid is kind of emanating, you might say, spreading out from, the whatever region you're talking about. And per unit volume, of course, but that's why it represents that sort of outward flow aspect of the fluid, because that's what this is. Okay. Let's see here. It also, there's the notation that we've seen before, div. When I saw divergence in math classes, I usually saw it written as div. And then it also goes by this notation. This is a little bit of a weird one. We've talked about this back in chapter 3 as to why that notation, at least algebraically, kind of makes sense. And, again, for your consideration, in my physics classes, I saw the del dot notation significantly more than I saw a div. Right? So heads up for that notation, extremely common. And likewise, in the comparison between these two terms, which term did I hear more often? In my physics classes way back when, I heard the term flux density more than I heard the term divergence, because it makes loads of sense. It's so explicit. It's so communicative of what it is. The word divergence is, it kind of conjures maybe this idea of a fluid kind of spreading out or something, but flux density just comes right out and says it. Right? Flux, understood to be boundary flux, literally says how much outward flow. And per unit volume is literally what we mean by density. So it's the perfect, explicit, completely transparent, no funny business terminology, and I really, really like this term, and especially for engineers, right? What y'all need most of all is to have good intuitive sense. I mean, obviously you have to know how to compute things, and obviously you have to know theorems and algorithms, etc. But I think you need to also have good geometric intuitive sense of what do things look like, so that you don't have to rely entirely on just algebra. Geometric intuition you should think of as being a guide that helps you make your way with algebra through solving a problem or working out some piece of material or something. So I think that is fabulous terminology to that goal. Okay. By the way, just like with Green's theorem, several names and notations for our newfound density. Okay. All right. Now, just to be explicit, and I'm going to let y'all read the details on this, but when I say that, flux should be thought of as something distributed through the interior, you can apply that very, very literally in the same way, now I emphasize, same way that when we were talking about the fundamental theorem of calculus, right? And we made this interpretation, I need the thing here. We made this interpretation of, if I can highlight, the derivative. Weird take, but we viewed it as being change density. It's telling you where change is happening, and I mean that pretty literally. You look at an example like this on the bottom left there of the screen, and I hope y'all remember that example, but obviously the function changes over the interval from 0 to 3, and it's a pretty reasonable question to ask. Okay, but with the obvious understanding that, of course, change happens in the interior. It happens between 0 and 3, not at 0 and 3. So where is there more change happening? Is it at the point 1 or is it at the point 2? Where is there more change happening? Well, of course, change density tells us where the change happens. Appropriately interpreted. And so you compute the change density and just look and see where it's bigger. So we're going to do the exact same thing here. Now the accumulating quantity is flux. Take this vector field and you can literally compute the flux through the boundary of that given ball. And I claim that's happening in the interior. Just, in some sense. And so, okay, in this sense of that happening in the interior, where is it happening more? Is it happening more at this point or at that point? And the way we arbitrate the question of where it's happening is we compute flux density. If you want to know where the flux is, compute its density. And you take that flux density and you compute it at your 2 points. And if you want to know where is more, then you just ask, which of these is bigger? Oh, by the way, it looks like it's that one. And so there's more flux happening at the point B. Right? It's just in the same way that the derivative tells you where change happens. Flux density, aka divergence, tells you where flux comes from, where that flux is happening. Okay. All right. So, pretty explicit interpretation of this term, flux density. All right. Moving along. Let me clean up my mess. And we put it all together. By the way, I hope the layout of how I have this written on the page looks familiar. This is, and I do all of this deliberately, right? I'm laying it out on the page the same way I did with Green's theorem, because I want to emphasize that this is morally kind of the same as Green's theorem. Different context, different geometry, different accumulating quantity, but underneath the big ideas are kind of the same. And so just like we did with Green's theorem, we have an accumulating quantity. Well, we have this quantity called outward oriented boundary flux. It's an accumulating quantity. The whole is the sum of the parts when you divide up the volumes. That's all that says. And stuff is stuff per unit volume times volume. That is, we plug in our recently developed idea of density, flux density in this case. And so, boom, we have ourselves a theorem. Again, strategically identical, right, to what we did with Green's theorem. This result here, known as Gauss's divergence theorem. One of the biggest theorems in this course, one of the main reasons that engineering requires y'all to take a course in multivariable calculus is to understand Gauss's divergence theorem. Not just to have memorized the formula, right, but to have a sense of, okay, yeah, but why is this true? What does this look like? And how can I sort of recognize it with intuition? So again, the big ideas here are to recognize that this is an accumulating quantity and that this is the associated density. Again, like every other integral theorem we've written down. Okay. All right. Okay, now I've got to say some little formalities here, and this is important mathematically. It's not going to come up super much that these conditions won't be satisfied, but it does happen. We're going to see an example of this happening coming up real soon, possibly today, I'm not sure. But it is important that the vector field be appropriately regular. It has to be not only continuous, not only differentiable, it has to be continuously differentiable. That derivative has to be continuous. It just doesn't come together if you don't have that condition. And when we say no singularities, that's kind of a way of saying, and I mean everywhere, right? So it's if there is so much as 1 point where this regularity condition fails, oh my gosh, all bets are off. Major catastrophes can happen at a single point. It's really surprising how delicate this theorem is. So anyway, very importantly, no singularities. Okay, coming back to that later. All right, let's get one under our belts. Let's get one win into the win column. Here is the example we're going to compute. We have a surface given. I missed. Surface given. We have a vector field given. And the question is to compute this flux. Now, let's recognize, I suppose, we do have explicit plug and chug, parameterize and pull back methods for computing a flux. So you could parameterize this sphere and then plug and chug. And that would be a horrendously inconvenient computation. Look at the vector field. Right? When you parameterize a sphere, there's trig everywhere. Trig or square roots, take your pick. By the way, when you have the choice, pick trig. Trig's better than square roots. Square roots are unfriendly. Trig allows you to take advantage of trig identities. And in the long run, you're going to find that is the friendlier calculation in a great many circumstances. Okay, so you parameterize that sphere, x, y, and z are going to be chock full of trig. Now look at the vector field, and that vector field would turn into a horror movie, right? It's an absolute nightmare of vector field. And then, of course, you've got the ds vector you have to compute, and that would be a nightmare of tedium going through all that nonsense. So this would be very, very, very hard to do the old-fashioned way. So let's instead notice that our surface almost a boundary. Really close to being a boundary. Now, this is one of the sticky wickets. This is important. You look back up here to the theorem. Yeah, that does pretty explicitly say boundary, right? Gauss's divergence theorem only applies if you're talking about a boundary. It only applies when you're talking about a boundary because the specific rules and conventions that we set up for how boundaries work and how orientations work are why we've got that cancellation that made it an accumulating quantity in the first place. The whole thing rests on it being a boundary. Orientations being critical to that. And so if your surface is not a boundary, forget about it. This theorem does not apply. Landmine. I've seen so many students get a little too excited, and they have some flux, and they want to compute some flux, and they just think, ooh, flux. I love Gauss's divergence theorem. I'm just gonna, immediately write it down as a triple integral. But hey, if your surface isn't a boundary, it's a bunch of nonsense. It makes no sense at all. It's complete garbage. And I've seen so many students step on that landmine, and so I make a big deal out of it because I've noticed over the years that the bigger deal I make about it, the fewer students do that, and the more success we have as a class. So, so there you go. Do be careful. It's gotta be a boundary. And again, looking back, here it is. Looking back to here, this surface, as defined, not a boundary. So we got to deal with that, and here's the good news. Even though it's not even though it is not a boundary, it's very closely related to a boundary, right? So the surface we actually have is just the opposite orientation. Opposite orientation of a surface that is a boundary. Right? We're one minus sign away from being a boundary. So cool. No sweat. We're gonna, doff the cap to orientation by including this minus sign and say, hey, having recognized that, S minus is just a minus sign away from being S, we'll throw in the minus sign to be honest about it, and then I'm going to work with S minus. Yeah? Everybody happy with that? Okay. By the way, when you make these arguments, again, it's very important, when you think about how you're going to write this stuff down on an exam, keep in mind it's not about the answer at the end of the page. What we're looking at, where points come from, right, is we're looking at your arguments. Your argument has to make sense. Each step along the way has to make sense. So throwing in the minus sign at the very end, or throwing in the minus sign arbitrarily at some point in the middle of the calculation, it doesn't make any sense, right? And so you do have to put the minus sign in at the appropriate place when you're introducing the orientation change, right? And I've talked about that at length previously. But anyway, just a reminder, make sure to put that in as appropriate. Now that we've turned the question into a computation on this blue S minus surface, no problem. That being a boundary, I can apply Gauss's divergence theorem right there. It literally is a boundary flux. Gauss's divergence theorem explicitly addresses that case. And so, boom. And now it's all over but the details. And let's see. Oh, whoopsie, I didn't mean to do that. I am apparently going to need to understand the divergence. Okay, so I've got to take my vector field. I've got to compute that divergence. Works out really nicely. Obviously, I arranged this example so that it would work out really nicely, so that I can, again, trying to make a sale here, trying to get y'all to buy into how awesome this theorem is. So I've arranged it to work out in a super convenient way. I'm not saying it always will. It won't always, right? But very often it does. And so, okay, in this case, we've got 3 plus x is our divergence, and so we just need to compute this integral. Notice the minus sign, by the way, coming along for the ride as it must. Right? And this integral is really easy to compute. Now, if you try to look at it as is, it's not so friendly. 3 plus x is not a constant. 3 plus x is not symmetric through any plane that the ball is also symmetric through. So symmetry is not on the table. Convenient little geometric observations not really on the table. But if you split it up into 2 separate integrals, right, then both of these integrals work out great. That's a constant on a garden variety geometric shape, so that's easy to compute. And let's see here. This one is 0 by symmetry. And do make sure to think through symmetry through what? Right? That's a little gap that I've left there for y'all to fill in. Keep in mind on an exam. You want to make a symmetry argument. Cool, I'm all for it. If it applies, right, you got to be right. There has to be a valid symmetry argument that you make your reference to. You don't have to do the details of the argument, but it has to be there. And you also have to explicitly note that you're concluding the integral is 0. You've got to explicitly say that you're making a symmetry argument, and you've got to explicitly indicate, in this case, what plane is it that you're claiming that there is a complete symmetry argument through. Right? So think it through. Good little exercise. Which plane makes this 0 by symmetry with a valid symmetry argument? Okay. Works out great though, and the nice punchline is an easy answer. Okay, so the heavy lifting of this computation, the lion's share of the work, you might say, was done right here with Gauss's divergence theorem. So I hope you appreciate the really nice benefits of Gauss's divergence theorem on this. Pausing. Questions? Okay. Let me just give you a little bit of a preview and then we'll call it a day. I'm going to show you some physical examples, and I think these are really important for a combination of reasons. First of all, that's arguably what you're here for, right? The whole reason that you are taking multivariable calculus, aside from the fact that it's required, right? So let's switch gears. Why is it required? Well, because it's super important for engineering, and it's super important for engineering because of how it shows up so much in physical, like really natural physical scenarios. So the first one I'm going to be talking about next time is this idea of a light bulb. And so when you have a light bulb, really small little LED type light bulb, well, it shoots out photons. And you can think of the flow of photons that it creates as being a kind of a fluid. Right? Not liquid, right? But it's kind of a fluid. It's a bunch of particles all moving kind of along with each other in some sense. So if you take the idea of divergence and apply it to this scenario, which we're going to do next time, then you get very natural interpretations. I think some really nice geometric satisfaction about the deep down interpretation of what divergence is in the first place. And it's a really good starting point and a really good metaphor for a lot of other cool physics that we're going to talk about. Y'all have a good rest of your day. See you later. Let's see here.